All right, so we're in 10.4. All right, here's number 13. All right, so in this case, you actually have to do a little bit of work on your own. Right, and some of this I asked you all not to worry about. Like for instance, trying to test for normality, we're just going to assume it works. But we'll touch on that just for a second when we get to it. So 13 reads like this: with the previous contractor, the mean time to replace a streetlight was 3.2 days. A city councilwoman thinks that the new contractor is not getting the job done as fast, so she selects a random sample of 12 street lights, right? And came up with all these different numbers from 6.2 to 4.3, all the way down to 2.6 and 1.7. Those were the times and days of getting the bulbs replaced. Okay, so that's the information we get from number 13. Right. So the first question I want to ask you all is, when we're doing these problems, are we talking about a mean or a proportion in terms of our data? What do y'all think? It is a mean, right? In fact, it actually says that in the problem, right? When it says there's a mean time, right? Now, it doesn't mean an overly aggressive type of time, right? It just means kind of an average amount of time, right? So if we're in the setting of using a mean, are we using z-scores or t-scores for that particular type of a population question? We are using t-scores, right? All right, so kind of keep that in the back of your head there as we start going through these things. Okay? So what we're going to do, at least for this one for number 13, is look at these numbers that were given to us. Let's see, in our data set. We need to calculate the average. And if you do calculate the average, you get 0.35. And then you need to take those numbers, calculate your standard deviation. And if you calculate that standard deviation, you get 0.481. Okay. All right. So here, if we're thinking about a test, the claim is that the old contractor took 3.2 days to change the light bulbs, and this councilwoman thinks that that number is now, well, the person's not doing as good a job, so that the number should actually be bigger than that. So mu should be bigger than 3.2. Right. So to do this test, let's get our test statistic. Right. So for here, we're going to calculate this t-score. Right. So for this t-score, remember we take, let's see. You know what? I made a boo-boo. Should these numbers have kind of concerned you all a little bit? Yeah, because I actually looked down at the wrong problem when I wrote those down. Okay. Yeah, the average in this one was 4.43 days with a standard deviation of 2.15 days. Right. So those should have been the numbers you got. Right. The ones I just gave you are for number 14, not for number 13. Okay. All right, so let's see. For my t-score here, again, we'll take our observation, 4.43, subtract the claim, which was 3.2 days, and then divide that by the standard deviation over the square root of my sample size. Right? In this case, my sample size was 12. Right? And if you throw that into a calculator, you get 1.982. I think it rounds to those 3 decimal places. Okay. All right. So that's my test statistic. So now we have to figure out is, what's the p-value, right? What's the probability that this sample would have actually occurred? Well, let's go to our chart and let's take a look at these numbers. Let's see. Where did I put that one? Ah, there it is. All right, so in this case, if you remember, n is 12, which means my degrees of freedom is 11. Right? So what I'll do is I will go along that row, right? And my test statistic t was 1.982. And if we go along this row, 1.982 falls between these two numbers right there, right? Which means the p-value falls between here and here. So the p-value is 0.025 is less than p is less than 0.05, right? At least from our charts. Okay, so let's take that info and go back to our problem. Right? This p-value was between, what did it say, 0.025 is less than p is less than 0.05. And if we look at our chart, 1.982 kind of falls almost in the middle of this, which means the p-value is probably somewhere in the middle of that, like a 0.03 or 0.04, something like that. Okay. All right, so now this question on 13, let's see, the wrong page, says, is there enough evidence to accept it or reject it at the alpha equals 0.05 level? Right. Well, if we looked at my p-value, we have to look at two things. Is p bigger than alpha, or is my p-value less than alpha? Right? If the p-value is bigger than alpha, then we do not reject. If the p-value is less than alpha, then we do reject. Right? So, based on these values we've got here, do we accept or do we reject my null hypothesis? Which is bigger, the p-value or my alpha value? I'm sorry? Right. You bet, right? So that p-value is smaller, which puts me in this case, which means we do reject my null hypothesis. Okay. All right, who asked for 13? Okay, and I'm sorry, I don't have my picture up. Is that Emmy? Is that right? Oh, Lexi, okay, I'm sorry. So, Lexi, what was your question on it? Yeah, so again, the thing to remember here, first of all, is when you read through the problem, ask yourself, is it a mean or is it a proportion question, right? Because the mean tells me to use a t-score, the proportion tells me to use a z-score, and that'll kind of inform which charts I need to use and how I get my probabilities. And then, like for instance, in this one, you may need to try to remind yourself how to actually calculate the average and standard deviation too. Sometimes they're given to us, but sometimes if we're just given the raw data, we have to do those things on our own. All right, anybody else have a question on 13? Here's number 14. Right, and we do have to do a little bit of the same stuff we did last time. So for 14, it says, according to the research firm, the proportion of individuals, right? So for 14, we're talking about proportions, right? So are we thinking T statistic or Z statistic for these? You bet. All right. All right, so let's keep on reading here. It says the proportion of individuals who text is 0.26, right? So the claim here is that P is 0.26, right? And then it says, suppose a random sample of 60 individuals, so N is going to be 60, and they're asked if they text or not, where they say 0 if they don't, and then 1 if they do, and we want to collect our data and test this against the alpha equals 0.05 level, right? So for this one, let's think about the null hypothesis, right? It's that 26% of the people text, and if we read through this, the question is, do the data, I always love that because data is considered plural, so it's always fun to say it like that. Do the data contradict the results of this information? Right? So for my null hypothesis, I'm not asking if it's bigger than 0.26 or less than 0.26. I'm just asking if it contradicts 0.26. So in this case, I'm just asking if the proportion is just not equal to 0.26. Okay. All right, and then in our data, we've got all kinds of zeros and ones there. We've got 60 of them. Right? For this one, if you add them all up and divide it out to get your average, whoops, sorry, shouldn't be using X bar here since we're talking about proportions. Right? I get the proportion from the sample is 0.35, and then the standard deviation from the sample is 0.481. Okay. All right, so let's get my test statistic here. Right. So again, it's the sample proportion minus the claim over the standard deviation S over the square root of n. So in this case, it's 0.35 minus 0.26. Standard deviation was 0.481, and I'm taking a sample of size 60. And if we throw that into a calculator, I get, if I rounded it correctly, 1.45 is my z-score. Right. So if we look this up in the chart, and remember, since this is a two-tailed test, I want to find the probability of getting 1.45 and higher, and symmetrically down here, negative 1.45 and lower, and add those two parts together to get my total p-value. Right. So if we looked up the negative 1.45 in our charts, you get 0.0735. So due to symmetry, that's also going to be 0.0735. So my p-value, if we add those together, multiply it by 2, however you want to do it, I get 0.1470. Okay? And in this case, I'm testing it at the alpha equals 0.05 level. So the p-value here is definitely bigger than alpha. So does that tell me to reject it or not reject it? If that p-value is bigger, what do we do? We do not reject it, you betcha. All right, again, let's see if I can recognize voices. Quentin, that was yours, correct? You asked about that one? All right, does that make sense on how we did it? Okay. All right, anybody have any questions or concerns about 14? All right, what about some of the others from 10.4? You know, we can either set up or walk through. So here is number 9. On the right page here. All right, so in this one, we're talking about some tats, right? So in 2001, 23% of American university undergraduate students had at least one tattoo, right? So in this case, right, we're claiming that our proportion P should be 23% or 0.23, right? And I got to be careful with how I say that, so I'll look at it here in just a second. A health practitioner suspects that the percentage has changed since then, okay? Let's see. So she obtains a random sample of 1,026 students, right? And the number that had tattoos were 254. Right? Is this sufficient evidence to conclude that the proportion is different from 0.23 at the alpha equals 0.1 level? Okay. All right. So again, the first question we have to ask ourselves, are we talking about proportions or means here? What do you all think? Yeah. In fact, it says it in the book, right? At the very end of the problem, it says, is there sufficient evidence to conclude that the proportion is different, right? So in this case, the null hypothesis is going to be that the proportion is 0.23. The null hypothesis, let's see, she wants to test to see if the proportion is just different from 0.23. So it's not bigger, not smaller, but just not equal to. So that's my null hypothesis. And if we're doing proportions, again, are we talking z-scores or t-scores here? Thank you. Yeah. So let's get our test statistic here. So my z-score is again going to be p hat minus p over the standard deviation over the square root of n type of a thing. Right. In this case, what's p hat? It's the number of successes over 1,026. And if you divide that out, you get 0.248. And now what about my standard deviation for these samples? Right? So to get my standard deviation of p hat, if you remember what we do is we take the square root of p times 1 minus p over n. In this case, to get this standard deviation, what number do I use for p? Do I use 0.23 or do I use 0.248? Which one do y'all think we should use for this case? Yeah, and why do we use the 0.23? What's our rationale there? Well, the whole idea is that we're trying to disprove the null hypothesis. So we're going to make that as hard as we can on ourselves. So we're going to assume that the claim is true and go from there. So if we're assuming that the claim is true, we're assuming that P should be 0.23, right? Not our 0.248. And then if you divide all this out, I think you get 0.013, right? So that's the number we can use in that denominator over there. All right, so for my z-score, it's going to be p hat, which was 0.248, minus the claim, 0.23, over the standard deviation for these samples we just found, 0.013, right? And that gives me 1.38 as my z-score. Right? So again, what we'll do to get our p-value is we'll find the probability of getting this z-score and higher, and since it's a two-tailed test, that z-score and lower. Right? And again, if you look these numbers up in your chart, this probability is 0.0838. This probability is 0.0838. So if we add those together, the p-value is 0.1676. All right? And we're testing this against alpha equals 0.10. So if we look at our p-value and our level of significance alpha, do we reject H naught or do we not reject H naught? You are correct, because the p-value is bigger, right? So since p-value is bigger than alpha, we do not reject H naught. Right? Because what this tells me is that this sample, if their claim is true, happens almost 17% of the time, like 1 out of 6 times. Right? So that's not out of the ordinary whatsoever. Right? So there's no reason to reject it at this point. All right, who asked for number 9? Okay, all right, Maggie, does that help out? All right, and let's see. Was 4 the one I was hoping you would? Well, I want to talk about number 1 just for a second as well when we get there, right? So here's number 4. Let's see. In this case, we're taking a simple random sample of size 65, and it's drawn from a population. Don't care if it's normal or not, since I'm taking a sample bigger than 30, we can still use this stuff. The sample mean was 583.1. The sample standard deviation was given to us at 114.9. Right? And the question is the population mean different from 600? Right? So again, the claim is that the population mean is 600. So since we're talking about means and not proportions, we'll use mu. Right? So the null hypothesis is that mu is 600. The null hypothesis asks, is the population mean different from 600? So in other words, is mu really just not equal to 600? Right? So it's another two-tailed test, and we'll have alpha equals 0.0, not 0.01, but 0.1 when we want to test this out. Okay. All right, so for this one, let's see. Again, we're talking about means and not populations, which tells me I need my t statistic here. Right. So for this one, I will take the average from the sample. Let me write it out here. Subtract the claim and divide that by the standard deviation from the sample over the square root of n. So here, it's 583.1 minus the claim over the standard deviation of the sample over the square root of 65. And if we do that, I get a t-score of negative 1.186. Right? All right, so for this one, I took a sample of size 65, which means my degrees of freedom, which is 1 less than that, is 64. Okay? So this is our setup. Okay, so let's go back to the chart and find some p-values here. Okay. Now, if you look at the chart, I don't really have 64 on here, do I? Right. So let's use this line 60. Right. And I got a t-score of negative 1.186, but we'll use symmetry to help us out here. So let's use the positive t-score 1.186. Where's the bounds there? Looks like it's between these two scores. And And if we go up here, well, let me just shrink a little bit. If we go up here, that's between these p-values. Right? So the p-value is between 0.10 and 0.15. Right? So if we go back to our picture here, remember this is a two-tailed test. So I want to find the p-value of negative 1.186 and worse, and 1.186 and higher. And we found that this p-value was between 0.05 and 0.10. So again, due to symmetry, same thing here. So if we add those two together, I know p is somewhere between 0.1 and 0.2. Right? And again, if we look at my charts back here, if I blow this up a little bit, 1.186, it might be a little bit closer to this side, right? Which means it might be a little bit closer to this p-value, but it's still a little bit bigger than 0.10. Which means if we compare this to my alpha level of 0.1, okay, so again, if you think about your number line, there's 0.1, there's 0.2, p is somewhere in here, and I'm comparing it to an alpha level of 0.1, which is right here. So is p bigger or smaller than alpha on this one? Yep, which means since my p-value is larger, we do not reject. Okay. All right, so again, I'm sorry I can't see you all. Who was asking about that one? All right, so Lexi, does that make sense on how to do that one too? Awesome. All right, anybody else have a question about number 4? No, I just picked the closest one. Right. If we look at them, if we go back down here, right, once you start getting larger and larger sizes for your confidence, or I'm sorry, for your sample size, if you notice, these numbers don't actually change a whole lot, do they? Right. So even if I'd gone with 70 on this one, it still would have been right here. Right. So once you start getting larger samples, it's not going to make much of a difference there at all. I mean, yeah, the p-value would be a little bit different. Like the p-value for 60 degrees of freedom will be different from 64, but it's going to be a very small difference. All right, you see that one, Adrian? Yeah. Okay. All right, anything else on number 4? Okay, one thing I want you to do is let's look at problem number 1. Because again, the question we're really trying to hammer home here is when do I use a z-score and when do I use a t-score? Right. So let's look at number 1 for a second, and let's talk about it for a second. All right. So for number 1, it says we have a simple random sample of 19 people. Right? And it's drawn from a population that's normally distributed, so that's good. So since it's a small sample and it comes from a normal population, we can use these methods. Let's see, it says the sample mean is found to be 0.8, and the sample standard deviation is found to be 0.4. Right? So when we read through this, when you look at it, do you all think this is a proportion problem or do you think this is a mean problem? Right? Because again, if it's proportion, that tells me to use a z-score. A mean tells me to use a t-score. So when we read through number 1, if you all had to guess a proportion problem or a mean problem, which one would you all go with? Well, if you look at these numbers, and that's why I asked it, because honestly, when I did it the first time, I messed it up because I looked at those numbers and I thought proportion. But look at how the problem is stated. It says the sample mean is 0.8. Right. And what I wanted to point out to you all is that a mean could also be a decimal. Right? A mean doesn't always have to be some big number. Right? I mean, I could have a mean of 0.8 or a mean of 0.2. It does not have to, I don't always have to have a mean of 25 or 30 or anything like that. So just make sure when you're reading through these problems, look at the wording carefully. Do they tell you that you're working with a sample mean, or are you working with a sample proportion? Because the first time I did this, I just saw those numbers and thought probably what you all did. Ooh, 0.8, 0.4, I'm going to use proportions. But when I went back and read it again, it told me the sample mean was 0.8. So for this one, the null hypothesis would be that mu equals 0.8, right? And the null hypothesis, if we're trying to see if it's smaller than that, would be that mu is less than 0.8. All right. So again, just something off the top of my head I wanted to show you all. Make sure you read through there and know, are you talking about a proportion or are you talking about a mean? And the numbers really don't indicate it, right? Just make sure you read through it and see how it's presented in the problem. All right, so anything else from 10.4 that we can yap about? No. All right, let me look at our Moodle site real quick. If you look, and let me get out of this.